We are very glad to have you. You
Yeah.
can share your. The debate will begin. I will ask you some questions to make a more to make this article that you published recently more reasonable or more people can know it more. So let's begin. Our first, you can share your slideshow if you want. My first
Okay.
question in the scientific background and research vision. To set the state, I would like to begin with the scientific motivation behind this work. What inspired you, Mr. Ivan, to investigate Ugandan propolis using advanced metabolomics, and what critical knowledge gap were you aiming to address in natural product research? I mean, what's also the key innovation of integration metabolomics with computational chemistry in your research? The question is long, but the mic is with you, Mr. Ivan. You can begin.
Okay. Thank you so much, Heba. First of all, this is my title. I'll have this like it will be like an interactive session, and of course, so I prepared some slides like basing on some of these questions the way they were prepared. So, what was my motivation? There is a lot going on in natural product sector, and the people are into plant research. In Africa, people do not delve so much into the microbial parts, and there are also natural products from different sources, such as bees. So these bees make more products known as bee products, which include like propolis, honey, and bee pollen, royal jelly, bee wax, and many more others. Even venom is so inclusive. So there is, of course, a lot of studies which has been worked on other bee products such as honey in Uganda and also all over Africa. So, but one of the studies, one of the missing component was the propolis. So now, and I came up with this kind of motivation by looking at how propolis is being utilized, in Uganda as a medicinal product. So if you moved, one of the motivating factor was like after looking at every, pharmacy or any other herbal shop, you find this propolis being packed, in different containers in form of tinctures, these alcohol made solutions, and it's sold for, medicinal purposes such as flu, cough, another upper respiratory infections. Some of it is also used for wounds, for treating wounds. Others even go ahead to use this propolis for cancer-related conditions. So, or even managing inflammation. So you can see there are also some other researchers who had gone ahead to prepare this propolis into tea bags, yeah, in Uganda, that is from Makerere University, and that was like of great interest. This product is being utilized in the community, but you can see other people also could pack these kinds of tinctures, in their homes. Then you just sell, no quality control process. You don't know what is inside the propolis. So that was like kind of, curious for me, and that led to, of course, to my curiosity. From my curiosity, I really went ahead to find out what are these, medicinal uses really documented. Are these medicinal uses for propolis actually documented in Uganda? Yes, if you could Google, you would find, yeah, propolis is being used for this, it's being used for this all over, the world. But if you try to look at the country, there was no evidence, for the country in Uganda. So I decided to carry out a simple survey, which was online based using Google Docs, and I wanted to know how people use propolis to confirm that kind of, mysterious curiosity I had in my mind. So I did that in around May last year, and it ran around 3 months, and I got about 200 respondents telling me how they use propolis. And indeed, they told me most of them said, okay, we use it for coughs and flu and many other conditions. So I had to write something about it, and you can see that link This is a Daily Monitor, one of the newspapers in Uganda. So I had to write a small story about propolis, and how it is used as medicine, So I designed that and I submitted it, and it's there online. You can find it. So that story now motivated me to think about, okay, what else is being, you could see this is a simple, like I just took a screenshot from the survey. Like you could see 58.2% of the respondents utilized propolis as medicinal agent. And most of them you used it for colds, coughs, wounds, and also burns. So now the question was, what is in the propolis? What is making this propolis, be active on these medicinal conditions? So the question for that, the answer for that would be now the chemistry. So linking the chemistry with the disease and the biological activity. So I tried to look again out on Google to see what has been published, on Ugandan propolis, the scientific work. So I found out that there were a few studies. One from my university, there was some undergraduate group which had done some antibacterial activity on propolis. Then there was also another study which had done on memory enhancing effects, and also another one had also looked at, actually it was the same author who did on memory enhancing effects. So now, but in all these studies, there was no detailed chemistry. We wanted to know which classes. There was this classical phytochemical screening of flavonoids present, alkaloids present, terpenoids present, sugars present, but there was no that deep analysis of the chemistry by using, the analytical techniques such as the GCMS, the LCMS. So this was the motivation for me. So I had to write a proposal for my PhD. I started now thinking that way from that abstract. So I started designing my proposal and I called it chemical profiling of Ugandan propolis and this activity against multi-drug resistant bacteria. So now I started generating the chemistry from zero, and this is how far we've come. Thank you so much.
Thank you, Mr. Ivan, for this insightful answer. My next question, considering the extraordinary chemical complexity of propellers, how do you see metabolomics reshaping our understanding of natural product diversity beyond traditional phytochemical approach? And do you believe that computational metabolomics and natural product chemistry could play this major role or play a major role in addressing global antimicrobial resistance and how does the integrative workflow redefine the modern natural product discovery compared to classical phytochemical isolation approach that is known by the wide group of people in this field?
Thank you so much, Gad, for that nice question. So once again, I want to dive into how metabolomics, of course, has shaped or is gonna shape or is trying to shape natural product chemistry. First of all, metabolomics involves use of different techniques, but most especially the mass spectrometry and coupled with the chromatography. So you realize that those days, the traditional approach used to be isolation, structural isolation, then bioassay. Like you first isolate, then you do the structure, and then you know what the structure does. So that was the traditional approach. Then there's this new modern approach which is coming up, which involves like global profiling, like you do, untargeted profiling, then you do network annotation, then later you test in silicon, then you choose what to go with and what not to go with for other bioassay guided isolation purposes or maybe our bioassay activity. So there is a diagram here I want to show you. So this is the first approach, which is the bioassay guided isolation approach, which was of course the classical approach, and people could normally go to extract, then they screen, fractionate, then they do by SE. Then after they purify, then they again do by SE, then they isolate, and then they confirm activity. So now there came this metabolomics approach, which has, of course, which follows kind of a different approach. You do the extraction, you fractionate, you can either use maybe ethanol or maybe ether or maybe extract, then you go directly to the analytics part, either LC-MS or maybe NMR. Then you go straight to BioSE. Then from BioSE, you could do the common metrics, then you go for feature prioritization, or you choose which compounds to proceed with, then you look at that to choose the active compounds. But now there's also another approach which is joining the two, which you call the integrated approach. So it's joining the metabolomics and the bias guided isolation. So here is now you see it involves in the both candidate prioritization, then by essay validation, and later you confirm activity. You do this by avoiding a lot of some other compounds which may not be of interest. For example, personally, I'm targeting antimicrobial activity. Like my assay is antimicrobial activity. But from my analysis so far, there are quite a lot of compounds which actually have been documented in literature to have anti-inflammatory activity in propolis. For example, the terpenoids. So now, and if you look at most of them, they have been documented not to be having a lot of antimicrobial activities. But again, these extracts or these components work hand in hand. There's a kind of synergism, and you can't say, okay, this is what works, but at least you have an approach. At least you have some clue that flavonoids do better, or maybe diterpenes do better, or maybe triterpenes do better. So for my case, I am now choosing the antimicrobial path. So this metabolomics shaped. In the next slide, I think you will see that some of the compounds which I managed to annotate, at least most of them have antimicrobial activity. So now I know at least what route to take. Yeah, thank you so much.
Thank you for this thoughtful perspective. Now let's move toward the strategic design of your research, the research design and analytical strategy. What were the central objective of your study, and why was an untargeted metabolomics approach the most suitable strategy in your study?
Thank you very much, Gad. So my main objective was, of course, doing untargeted, because I really didn't know what was inside there. I could say how I was motivated. One time I had an interview with one of the panelists who were actually supposed to give me a scholarship for my research stay. And the same professor asked me, so what is in there in the propolis? So when I told her that I am going up like open-minded, I want to do untargeted, I don't know what is there. So she was happy and she clapped for me in that panel. So meaning she already knew that propolis is kind of complex, and when you say, okay, I'm looking for this and I'm looking for the other one, you may not exactly do that unless you have some clue. So in this case, I really chose untargeted. I just wanted to go open-minded to know the wider chemical space of this propolis. And then also, this kind of untargeted metabolomics helps you to identify the rare metabolites. There are some compounds which, of course, are not existent in any type of propolis, but this, of course, also depends on where these bees forage. So where these bees pick the resins and other components. So of course, I also wanted to come up with a kind of structural clustering to know maybe which kind of group has a lot of clusters, for example, phenolic acids, phenolic compounds, flavonoids, and many other types, or terpenoids. So in this study, we kind of had, you can see there is my pointer, laser pointer, okay, laser pointer. So you can see here, this is like something I summarized, the summary of the classes of compounds we annotated. You could see like flavonoids were the highest, followed by the terpenoids, followed by the phenolic compounds, followed by the lignans. Then the others were like the rare ones, such as megastigmins, which is unreported in most of the propolis propolis studies, and also the chromones and stilbenes. So these are some of the rare classes of compounds which have been detected in the propolis. And also the other point was now, if you look at this, we have kind of a lot of complex stuff, you know. So all these once again depend on where the bees forage. Yeah. So you could see this is one of our our molecular network. So we pulled out some of the key clusters. You could see the ones in the yellow one or orange. These are some of the clusters or some of the nodes which share a similar which share similarity in chemistry. Then the gray ones, the ones you see here, are not kind of related to each other. So this is our general molecular structure, which shows a lot of connections. Then there are these singletons, which are lying down here, which don't have any kind of connection. So meaning they cannot be related to any other, kind of network inside here. So they stand alone. So this means they cannot be identified. Like it's kind of complex. So this is one way of really coming up with the idea that Ugandan propolis is also complex. So we need to go deeper and maybe use other techniques, maybe try to monitor at what time, maybe the factors which contribute to this, and maybe some other studies could go deeper in looking at maybe the botanical species and also maybe the climate factors and many more others. Yeah, thank you so much, Gad.
Our next question. In a complex, there is some question that put by the audience in the previous part that you have already explained. What do you mean with the computational metabolomics, and do really metabolites include unknown metabolites? In the chat box.
Let me check on it. Okay. Thank you so much, Adele Gadala, for the question. Yes. So now here we are looking at maybe this was supposed to be the next step, but it's okay. I can tackle it. Here you're looking at having data analyzed by, for example, I can say LC-MS, and now you try to annotate this data with available libraries online. So there are libraries which are present or deposited. People do different work, different analysis elsewhere, and they deposit this kind of, chemistry libraries. And so now you deposit your spectra, and this spectra is matched against these kinds of libraries. So these libraries help you in kind of identifying some of the components which are present. So you do this in a computational way. So, but first of all, before going to that, you have to process your data. You just don't deposit it like that. So that process of doing the data pre-processing, it's a computational. You use like different coding methods. There are some automated mechanisms which you need to do, and I think that makes it computational. Yeah. Then the other question was. Do rare metabolites include unknown metabolites? Now, no, of course, unknown metabolites are not, of course, included in the rare metabolites. Here, in this case, we described rare metabolites as those which were like not presented in the propolis chemistry ever through literature screening. So we did a literature search and we found out that some of the components were not present in propolis, but they were present in some of the plants. We had to compare that kind of, botany chemistry relationship. Yeah, thank you so much.
Our next question. In complex natural matrices, capturing the widest chemical space is it challenging? How do your analytical workflow balance metabolites coverage, sensitivity, and selectivity while minimizing analytical bias. Also, what were the reasons selecting LC-HR-QTOF-MS, and how did your ionization strategy enhance the metabolite detection across chemically diverse compounds?
Okay, thank you so much, Heba, for that. Don't know why my screen is not moving. Don't know. Yeah, cool. So this is what we did. So we used, of course, a powerful instrument provided by Bruker, which is the ultra-high performance liquid chromatography. The ionizers, we used the electron spray ionization, and of course, it was high resolution with the mass analyzer that is quadruple time of flight, in fact, 2. So this instrument, of course, has the strongest sensitivity with a resolution over 60,000. And to enable that, we capture quite a huge number of compounds with huge masses, of course. We had to set our instruments to at least cover an MZ range of 50 to 1,500. So that was really enough to capture our metabolites. So we used both positive and negative ionization mode. So, but of course, when you look at your data, after the analysis, you can tell and see, okay, the positive gives more, metabolites compared to negative, and that has been always most of the case. And so I had the negative. I analyzed both negative and positive. I had to process them differently because you cannot process them at the same time. So when I did that, I looked at the metabolites which are being annotated by the positive mode. Most of them were passing my criteria. In this case, you need to develop your own criteria while coming up with this. So you need, for example, if there's a score which is maybe between 0.6 to 1, or maybe probability of 0.7 or 0.9 to 1. So you have to make sure that all your metabolites surely reach that level. If not, you discard. Even when you know it as a plant compound or plant metabolite, but if it does not really make up to that probability, you just discard it. So for the negative, for sure, it did not really make up to the point. So I had to discard that data, and I had to proceed with the positive mode data. So most of our analysis we used, of course, we had replicates, both the biological and the technical replicates, during, of course, our sample collection and also sample preparations. So our mass accuracy was high, and it was at least better, around greater than 1.45 parts per million. And also we had a nice gradient. In this case, we developed our gradient using the HPLC before going to this very expensive and the complicated technique. So we used two solvents. One was, of course, the non-polar, capturing part of the non-polar, and also the polar. So you could see we had to arrange. So as we go on, I will show you how we had to minimize, to have the kind of flow and the elution patterns, and we had to capture most of the metabolites. So on my right, there is a diagram which shows the precursor masses. It's like a scatter plot. You could see that at different retention time, you see a lot of, points having certain masses at certain retention times. So you could see most of them were actually between 150 to around 650. They were around here. And also, you see, we had also a nice retention time up to 70 minutes for the LCMS. So that's really captured a lot of metabolites. So down here is our extracted ion chromatogram, which we generated from enzyme. You could see, so the colors, different colors show different, this is a chromatogram. It shows the different peaks from the different samples. So I had 27 samples, but of course, when you're doing this, you code them, and most of I had, of course, the biological and also the technical replicates. So, but these represent all the samples I did for my agroecological zones. So you could see here there is this yellow one which represents, for example, a sample from one district in Mbarara. So you could see another one here. So most of them at least showed that they are not so much related, but at least they have some similarities to some extent. Yeah, thank you so much.
Okay, Mr. Ivan, we have two questions in this part. What from Dr. Adil? What is the software that you use online or just it's on online website?
Okay, thank you so much, Del. Yeah, these softwares are actually open access. I think that's the right word to use. Um, in this case, we used MZMine for data pre-processing, and all these are snapshots from NZMine. So in case you know how to use NZMine, I'm sure all this information you can surely obtain from there. I think that also in the next slides or maybe next questions, I think we will be able to go deeper into the computational approach and how we did it. I think you can be patient a bit and wait. So thank you, Ivan. Why must we do this? Is there any criteria we could use this select? Are there any criteria we could use to select the MS? Yeah, so if you're doing untargeted, for sure you need to be open-minded. I said this in the beginning, but if for example you are doing targeted and you know most of your classes of compounds maybe lie in a certain mass, you can always do that in the software in the analysis. You reduce that MZ range. So for me, I was doing like untargeted modes. That's why I had to leave it open. But for targeted, you can always, know your range, and you just give it, for example, maybe 50 to maybe 500, and most of your metabolites will be detected. Yeah, so the link is there, mzio.com. You could also get it from GitHub. It's actually free, so you can access it even when I think you need to have an institutional email to access that MZ-Mine. It is free. Okay, thank you so much. I think the questions are done. Heba, you can go ahead.
Yes, you can go ahead. Now that you understand the research framework, let's move into the practical aspect of the sample handling and preparation. How were the propolis samples selected, and what extent did environmental and geographical variation influence your study design?
Hey, thank you so much, Heba. First of all, Uganda is endowed with great biodiversity. Those who have not been to Uganda, you need to visit. You see how we are gifted with a lot of medicinal plants and biodiversity. So my study based on before I go to that, propolis chemistry normally is affected by quite a different number of factors. Not only the chemistry, even the activity, which I'm yet discovering whether geography affects that. So, but for chemistry, I based on location, geographical location. So I picked most of my samples from different geographical locations. So you can see the Ugandan map is on my right here, and you could see the different colors represent the different districts where I picked my samples. So then you can see Kotido is in the northeastern part of Uganda. This has a lot of, it's actually the no, it's semi-arid. It's always most of the time dry there. So if you come to Adjumani, it's also somehow balanced. Then if you come to Mbarara, these ones they receive a lot of rainfall. Same applies to Masindi and also Nakasongola and also Kibuku. You see, this was my sampling range, and that affected my study design. Also, if you look at my left-hand side, I put a simple table here showing you some of the factors which could be contributing to the geographical variation. For example, if you look at the districts, Nakasongola, which is in the Lake Victoria Crescent zone, is normally dominated by wood savanna and forest. If you come to Masindi, it has a lot of also forest and savanna. If you come, for example, to Kotido, which has arid savanna and sparse woodlands. So all these types of vegetation, and also if you look at the rainfall and the temperature ranges, all these contribute to the vegetation growth. So that means also the bees will also pick where to really go and forage. So if the bee cannot move from one district to another, much as they move miles over 15, but in this case, I'm sure they do not cross districts. Like, you go to another district. So I'm sure here they foraged from different medicinal plants. Of course, you find some of them are distributed in most of the agroecological zones. I'll give you an example of Bushen here, Mbarara and Rampara. These are kind of close to each other, so meaning they could be having a lot of vegetation, similar vegetational, growth. So that means if in our studies you find that most of the chemistry in this area is actually similar to each other because of maybe the botanical species which are present. Yeah, thank you so much.
Hey, Mr. Ivan, there is a question. I think it is from the previous section from one of the audience, Dr. Mahmoud Freeland.
Okay.
Could you give us an idea of the sources of these metabolites? He means the propolis metabolites. Are they only collected by bees from various plant or special monofloral, or are they are special transformation of certain metabolites within the hive using bee secretions? For example, it is strange to find alkaloid in propolis. Thank you very much.
Oh, perfect. I like that. So bees forage different medicinal plants. I like that question always. It comes up in most of my
The
presentations.
mind is a
So
creative one.
yeah, so bees forage different plants. Actually, in this call here, I have one of my field assistants who supported me in we were together in collecting some of these resins. During my study, I would actually identify, even like using, I would ask the beekeepers, do you know where these bees visit? Do you know some of the species they visit? Do you know where these bees pick some of these components? So they would tell me some of the species, and surprisingly, we'll be knowing most of these species. So it depends. If a bee visits a species which has alkaloids, and for example, a resin has some components of alkaloids, maybe it visits nectar, maybe it visits some other plant components which has alkaloids, and it comes and seals the beehive with this kind of components or resin, automatically you will be able to detect that same compound in your propolis. So basically, propolis is composed of resins. 50% of propolis composition is full of resins. Yeah. So, and this, of course, these resins come from plants. And if you read my papers, actually, there are two papers. The first one was on GCMS. So this one is on LCMS. So the GCMS one, of course, was looking at mostly the volatile components. So if you look at most of the components there, they were being linked to eucalyptus. So these bees visit a eucalyptus species, like for example, Eucalyptus camaldulensis, which is kind of similar, common in Uganda. So they would visit this. So we linked that, and we linked the discussion with the presence of these species in a given area, and you could see that, for example, Bushenyi, which is in western Uganda, it has like lots of monoterpenes, lots of sesquiterpenes, and most of these compounds have been detected in eucalyptus. And indeed, the eucalyptus is also being grown there in the same area. And if we date back in my study, of course, I have a document which has all the species. We could document eucalyptus has been recorded in Rushenyi. Eucalyptus has also been recorded in Mbarara. So we would also go back. So during my analysis and discussion, I went back and checked whether the same species was also noted down. And indeed it was. So I linked the discussion, but this needs, of course, confirmation. And this is another type of study. So for me, it was like a kind of discussion, but looking at the geography. So someone else can now do the DNA barcoding to now confirm by looking at the resins and then also the propolis to see whether this Eucalyptus camaldulensis is the principal source of the resins for the propolis. I hope I have answered that. Thank you.
Okay. Question from Dr. Jimmy. Thank you, Mr. Ivan, for this information. Is there is a correlation between the geographical metabolites variation to the biological activity? If so, which district has the best propolis in terms of phytochemical profile and biological activity?
Is this a question from the chat?
Yes, yes, from Dr. Jimmy.
Okay, thank you. Oh, is there a correlation between geography? Okay, thank you, Dr. Jimmy. He's one of my colleagues, actually. Yes, now, this is the initial phase of my study. The chemistry, yes, there is a geographical variation. And now, right now, actually, I'm in the lab, not in the lab right now, like I'm now doing in vitro studies. So I want to see whether propolis collected from Bushenyi has also different activity compared to propolis collected from Cotido. So that's what I want to confirm. But the chemistry part is already clear that there is a variation. But the bioactivity part in vitro is what I'm actually discovering. I guess when we are done, that paper will also be out at least for the public. Yeah. I think there is a hand. I saw someone with a hand up. Jeremiah Ekibitenga had a question. I saw his hand up. I don't know.
The last one who asked a question is Dr. Jimmy. The one of Dr. Mahmoud Swelem, one replies to it, so it's here in the last of the section. So let's complete the journey. Let me give you a one deep question. Natural matrix like propolis often present extraction and reproducibility challenges. What were the most critical technical obstacles and how did you optimize your preparation protocol?
Thank you so much, Gad, for that question. Yes, actually, I have to be frank with you. When I started my lab work, I thought everything would be easy, basing on the literature I was reading. So when I joined the first 2 months, and the first 2 months was like kind of hard for me. I was dealing with propolis for the first time, and I didn't know that this propolis had different physical properties. So I was reading a lot of papers from Brazil, from China, from Europe, and they're like making it kind of easier to work with. So I didn't know that there are a lot of differences in the gums, for example, in the resins. So most of these resins have different physical properties. So when I joined the lab, I don't know where my slide. Okay, cool. So when I joined my laboratory analysis, the first step was, yes, I have the gum, as you can see here. That's how I collected it. And in the sample collection, one of my field assistants here can tell that we used to, squeeze it together and make like a lump. So when I came to the lab, it was difficult, very difficult to make it into powder, as you can see the final picture there. So what happened was, the first challenge we realized was we didn't know that there is a lot of variation when between using a homogenized propolis and also the gum itself. So we started with the gum itself without making it into powder. So I got this, just scrapped a bit, and went straight. Like I told you, this is the GCMS was my first laboratory work. So that paper is out also. So the LCMS was the second one. So we performed a lot of GCMS, and we wanted to see whether there is a relationship, whether there is a variation in the distribution of compounds between when you homogenize and not homogenize. So the highlighted one was the unhomogenized one. So we started with a small amount that was around 100 milligram per mil, and we did the put in the headspace, and we had to heat and analyze. So now I went back to the Excel, started now analyzing, looking at what I've matched with my software, also the NIST database in the GCMS. So I started comparing, and later on, I realized that there was not, this is just an example, there was a lot of variations, you know. So then I later had to grind a little amount of this propolis. So you can see the steps here. So grinding this was also not easy. So it took me like 3 months. I had 27 samples, and it took me like 3 months to come up with a solid method on how I could get this powder you see here on the last page. So I had to crush this. Of course, I had to add this liquid nitrogen here and then freeze at minus 80 degrees Celsius. Then, of course, I bought my hammer here. You can see I had to hammer this to crush this into smaller particles. Then I used the mill to grind this into this powder you can see. However, there was a lot of difficulties. You know, this propolis would solidify within 3 minutes. So so there are samples like 5 samples from some districts which could solidify within 5 minutes. So meaning it was going to get stuck into into the meal. So you have now to remove that gum. Again, you clean it again. You clean with, of course, with some organic solvent. Then you wait a bit. Then you go back and make powder again. So it took me like 3 months to come up with this. So then finally, I discovered the trick. And once I got this powder here done, I came back and did another setup of analysis on homogenized, and you can see even here the number of metabolites in the homogenized propolis were actually more compared to the one in the non-homogenized. So this was also nice. We did a lot of plots, scatter plots to see if there are kinds of variations among homogenized and non-homogenized. Then also, this is just the final amount we went with. We started with 40 milligram and 100 milligram to see also whether the metabolites are present in 100, more in 100 or in 40. So we realized that as we increase the concentration of the propolis, the metabolites also increase. So we had to choose the 100. You know, this is part of method development. So this took me like 5 months, 5 to 6 months. That was in the lab, and I was in the lab, and things were not going on well. But later we discovered this. So this was like a breakthrough for the next studies. So already we knew what to do, and after that we had to perform. So here I show you my HPLC gradient, which also took me some time because I didn't know the chemical nature because of the complex nature of this propolis. I had to also optimize this kind of HPLC gradient. Um, it took me like 3 months. All these were like obstacles, but later you learn, you read a different paper, you see what they did, and okay, you try it out, and tomorrow you look at the chromatogram, and the separation is not good. So later on, we zeroed out on this. You can see I could wait up to 90 minutes. This is just one sample. You wait for one. So I had different samples, and now here I was trying out the different solvents. But of course, I really wanted to back up the idea that propolis is being used as a tincture in Uganda, and now I wanted my research to kind of collaborate with the tincture related stuff, and so I decided to zero down on ethanol extracts. So this is the gradient which I developed later on, and then I optimized it in the LC-MS analysis. So this is how I had to. These are the obstacles I faced. So, but later we solved them. Thank you, Gad.
Okay, thank you, Mr. Ivan. As we discussed before, the analytical engine behind your metabolomics profiling the computational interpretation becomes essential. So let us move into your digital metabolomics workflow and computational metabolomics and molecular networking. Could you describe your data processing pipeline from raw spectral acquisition to molecular networking?
Yeah, of course, that's something I will also do. First of all, I would now want to, like I've discussed most of this in the previous conversations, but now, like I said, we performed both positive and negative ionization modes. So now, what I'm going to describe the next is only positive. So I decided to trash away the negative data and proceeded only with the positive. So in this case, we use MZMine. You all, at least I see in the chats, most of you know at least what MZMine is. It's one of the tools which is actually very important in data preprocessing, especially high resolution data for metabolomics. So this is the first step I did. So I obtained my raw data after analysis from Bruker impact to LCMS machine. And then the first step was to look at my data. Like, are there some peaks? Are there some peaks? You know, that's the first step for any metabolomist, someone who is into metabolomics. You really, the first step is to look at how your data has been generated. So that's the first thing I did, and this is just a sample. You could see here. This is one district, and it has, of course, some replicates as well. So I had to put all this data for the same district there. So this is D. This D you see is Bruker. It's like from Bruker generated data. So MZMine normally allows now the new versions, not MZMine 3. So MZMine 4 and above allows you to import directly raw data into the system. But those days you could first change or transform this data into MZML, which would really support you in the pre-processing. So this interface you see is for the MZMine. So here you can look at your data, you can do your feature detection here. You can also look at visualize your data here. There are also tools. There are many other things which you can use to really come up with an idea on how your data looks like. So here is our chromatogram. This is how it looks like. One of the samples looked like this, and you could see at least there is something in there. So if you clicked, for example, here, you would see a spectra. So this is a chromatogram. This here, you could see the chromatogram parameters. This side, you could see the spectral parameters of your samples. So after this, now after looking at this, there is a tool within MZMine, which is called the MZ Wizard. So now I had to go to MZ Wizard. It's down here. So MZ Wizard. So this MZ Wizard has also its different parameters. And because I use an ultra high performance HPLC in this part here, of course, you select your instruments. So there are a lot of instruments here, HPLC, GCMS, you can always select to create like a kind of workflow. So I also choose. There are also different mass analyzers here. So I use QTOF, then I chose my QTOF. So this is my workflow. So now there are parameters, different parameters, like under the filters, you need to know. For example, you need to know most of the cases, you will not see anything from 0 to around 1. This may not be really a compound or plant metabolite or it may be maybe a contamination or something like that. So I had to screen. I had to choose. Maybe I said 0. I want my retention time range to be between 1 maybe to 69 or maybe to 70. So this was done under these filters. So there are other filters. Most of them are actually automated. You can adjust them based on what you need. For example, the noise range. For example, the smoothing. For example, the chromatogram development patterns. So all that can be decided here. So there's also this part of annotation. Within MZMine, you can actually download different databases or libraries, and you add them into your workflow. So, but for my case, I wanted to to utilize GNPS and also SIRIUS. So I did not upload any library. But if you, so the current MZMine now, I think they have a lot of improvements. Now you can even perform SIRIUS within MZMine. You can also do all these annotations within MZMine. So me, I really wanted to just do it that I just wanted MZMine to help me process the data. So that's what I really wanted. So now from this case, I had to, of course, choose. When you reach this point, you have to choose what enzyme should generate for you. Of course, I wanted to do GNPS, that's the molecular networking. I also wanted to do SIRIUS, which is the in silico structure elucidation. So I had to tick all this. So you can see, so here you need to have a folder where you will import all this, and mind you, you need to have enough space on your laptop, and also your speed, the speed of the laptop needs to be very fast for you to accommodate this kind, especially when you have huge data. So this is what I did, and after this, of course, it depends. It took me my analysis, my workflow took like around 30 minutes, and I had to get my SIRIUS exports, my molecular network exports. So in this case, MZMine gives you data in different forms. So for a GNPS, I really wanted to come up with I really wanted the features which you are going to see here. Okay, I think that's the next. So here you see on top here, when the run is done, the feature list which has everything of the data, which has the retention time, it also has the area, the height, and other details of your data will always be here. Then if you added any libraries, the libraries will always show themselves here. So, but for me, I did not add anything. I just needed the feature list and my MGF format, which contains the spectral data. So I really needed the spectral data for my GNPS, and the SIRIUS annotations. So after that, I had, of course, to import. So this is my feature list. So after the workflow, GNPS, MZMine generates for you this kind of feature list. This feature list contains millions. Sometimes it could even freeze my laptop. So, and I wait. So it had millions of metabolites. So you can see there is the ID, the retention time. Now you could see from maybe 0 to 1, or maybe these are not surely plant metabolites. So the ID also could be there, the height, the other data files such as the area, maybe intensity. So for me, who was really interested in chemometrics, I really wanted the area as well, because for chemometrics, you need to import the peak areas of your metabolites. So this feature list was really very important for me to match my results from GNPS and SIRIUS. So I matched using the IDs from GNPS with these millions of metabolites here. So you can see this is the ID I use. So I could look at the ID here, and I go to my SIRIUS generated results, and I also go to my GNPS generated results. So I could match this and also match the MZ and also match the retention time. So there now I could pick that you could find maybe one of your interested metabolites is like maybe number 60. So all these are not part of your matches which have been generated in GNPS or SIRIUS. So this is a feature list which was really very important. So of course, after the feature list, now it's already generated. MZMine has generated for you your NGF file. So the next step is now connecting to GNPS. So there is always a file transfer protocol, which is the WinSCP. This is what I use. So here you import your data. So you can import your data, you connect, you have to download this. It's also software, graphical user interface software. You have to download it, then You install it, then you upload your data. For example, if you are on my left, this is your desktop, laptop, and this side is what you will see in GNPS. So you have to upload, of course, in your account. So I had to upload my data from here to this side, and then I went to GNPS. This is also an open source software, which is of course online. You can always create an account. So I created an account, gave my work a title, and then proceeded. So in this GNPS, I uploaded my components. One was my MGF files, which contained the spectral data. In this case, either MS1 or MS2, either MS1 or MS2. Then I also uploaded my feature list. Of course, this was also very important for matching, you know. So there are other parameters like these are the options, filtering options, which you can also perform. You can see like this precursor ion tolerance mass, which can be adjusted, fragment ion mass tolerance, which can also adjusted, but most of them have been like already performed and they are automated by some author who generated this. So there's no need to do this. So after doing that, you put your email where your work will be submitted. Of course, then you click submit here. So this takes some hours in case you have huge data. So mine took like, I think, like, was it like 1 hour? So I had to wait and it gave me the job. So the link is sent to your email. And when you click on your email, you come up with something like this. So here now you need to choose. What is important for you. So I really wanted to see the hits, the library hits, which have been surely matched from my data. There are also, for example, if you wanted to look at the molecular network with cytoscape, so you can see here on my right, how you can visualize. So this was the original network. So you can see a lot of singletons here which are not connected anymore. You can see some of the compounds here which are connected. The nodes are connected there. So you choose on what you really want to do. So after that, now I came to check on my library. So I had around 234 hits. But not all these are plant related. Your spectra can match with some other compounds which are not plant metabolites. So as a scientist, you need to know what you want. You need to do literature search. You need to, for example, confirm some of these. So these libraries contain, of course, authors, compound names, the databases they use. For example, routine here, someone used NIST for team library. So you can click here and view the raw spectra. You can also view the molecule, and also you can also look at the classes and also the cosine values and etc. The tension time, and also mostly you need also to choose here to have the criteria. So I had to choose like in a certain cosine range, metabolites which have this kind of value will be suggested or taken for further, analysis. So after that, I had now to choose. This is a curated CSV file after doing all the searches, literature comparisons, and what. So I came up with all this information. So as you can see here, not you are free to put what you want, but this is what I thought was really okay for me. So if you click on this, it can take you to that spectra, to that match in GNPS. If you click on each individual compound here, link here. So among the compounds I chose, this is just a screenshot. You can see there was rutin, isorientin, quercetin, mangiferin, which is a xanthone, carangin, which is a flavonoid. So you can see there's a lot of information here. But most importantly, you need to look at the shared peaks. So the more the number of shared peaks, the more the best that match is. So I will give an example here, like rutin has around 8. So rutin has around 8, isorentin has around 9. This compound here, which is an anthocyanin, has around 22. So you can always set this, but at least there is literature that anything which has 7 shared peaks and above, it can be, included into your putative matches. So that's what I really had to decide on. So then there is another step for in silico annotation. You know, both of these, now the SIRIUS doesn't work like now the GNPS. So the SIRIUS is something which is like going deeper. It's trying to find out more of what is left out, you know, from GNPS. So it is also an open source. If you have an institutional email, like you see here, this is the mass.ac.ug. So if you have a university email, you can access this free of charge. So I had to download this, and so I had to drop my MGF files. You remember from MZMine, I teach that I need a file which I will use for SIRIUS. So I did the same, and after that, I dropped my MGF file here, which contains the spectra, both MS1 and MS2. So after that, you can, I had now to, maybe I can, yeah, I had now to submit the job. This took me an individual, let me see, it took me like 4 days to come up with the final. So I could leave my laptop. I had a desktop and a laptop, so I put this on my laptop. So I left it there for 3 days, and it could, you know, perform, compute. You know, you need to have sufficient internet, and it takes time. So it performed that, and when I landed on it after the matching, so I had to look at metabolite per metabolite, metabolite per metabolite. Once again, you know what you want always as a scientist. So here I knew what I wanted. Of course, from this side here, you could always see, you could always click on an individual hit, and it gives you, for example, there is always an indication that it has weak, the chromatography is not good, like it's poor, like it has that part where it shows it's poor. So I would discard that. You could also always click on each, and you see that the chromatogram was not properly built, the peak is not clear, it's not well distributed, it's not normal. So I would delete that. That's part of data curation. So not everything generated automatically is true. So you have to go ahead and curate as a scientist. So after all this, I ended up with around 54 metabolites, 54 out of 300 plus. So this was really interesting. So here I am showing you what SIRIUS can do. So SIRIUS can help you to come up with, to generate a formula, the formula of that putative compound. It can also help you come up with the putative structure and also the classes, you know, of the compounds. So it can also go deep in the new version of SIRIUS. It helps you also to do deep de novo structural elucidation for stubborn, you know, compounds which really can't be found anywhere. So it goes deeper and suggests, you know, what that compound could be and where it could belong. So here it's now you could see the adducts. In this, I just selected one, so it's like a step by step. So the first thing is generating the formula, and you could see here there are scores. So SIRIUS basically depends on scores. So there's this zodiac score. So if it makes a zodiac score of 1, then also there's what we call, I will discuss that later, the CSI finger ID, which discusses which discusses the formula. So if you have a perfect match of 100%, probability of 100%, then that could be the formula. So you could see there are also other matches here which have the same kind of ionization pattern, fragmentation pattern, but they don't make it to 100. So here you could also check. So, and you can see the tension time also, and also the confidence. So some of course have confidence of around 0.1, maybe 0.009. So it depends on really what you want. So after that, the same SIRIUS can give you, like I said, a probable class of that compound by using the canopus. There's that feature called the canopus feature within SIRIUS, which gives you a probable structure, a class. So in this case, you take the level 6 class, which is here in green. So you could see, and you can also tell from from the zodiac, which has 100% here. So you can see the precursor ion is also represented well there. So the other step is looking at the structure. So this is generated by the CSI. Sirius also uses different software, I mean databases. For example, the lipid maps. So there is coconut, there's also Chebi, there's also Knapsack, Supernatural. Most of these databases are available. So it goes deep. So now this compound, which is a nutrient, you can see they are two. The first one is this, and the second one is avicularin. So you could see by looking at the CSI, so the more the negative here, the more the better the structure. So you could also, based on this, to choose which putative structure you can proceed with. So after that, of course, you can go ahead with de novo in case your structure is kind of hard to be detected. So the de novo does like more, there's a feature called MS Novelist, which goes into like searching for novelty in that structure. So the de novo also confirmed the same thing. And if you look at the substructure notations, you could see at least it generated something here. So these are some of the, for example, the final conclusions like it had generated. The inside key, of course, you have to confirm this also with PubChem. It also had the beta one here, the adductive there, and also the molecular formula. So you need to confirm this also within PubChem. You see whether this formula surely exists. Yeah. So after that, now, after doing all this one by one, you have now to curate. And before that, you need now to transport. So after the job is done, there are many options here. You can export summaries. You can also do a future-based molecular network. You generate an MGF from here, and then you go back to GNPS. But you can also get some summaries here. So because I've done GNPS already, so there was no need to do GNPS again. So I had to import. So normally here, you can choose. You either choose the best hits, or which is also recommended, or all the hits. Then you curate in the Excel, or you can always curate within the Sirius itself. So after this, I had now to come up with the CSV file. Most of you, this is present. If you check on the paper, it's the supplementary file. You can access it. So you can see how much time it took me to come up with at least something. So this is the curated file. So this curated file has, of course, some, putative. What I believe surely, basing on the structure, you can see formula rank 1, CSI finger ID, zodiac 1, ADAX, and many more others. So also the classes, so I confirmed most of this also with PubChem. So this is now what I proceeded with, for my, as a chemometrics. So now, after doing all this, I could match. You match the same thing with the feature list, which was generated in MZMine. So one by one, you match. The MZMine has millions of features, so you have to match. For example, you come here, choose this retention time, and choose the MZ. You match it with the MZMine. So you have to search one by one until you get. So if it matches, that means here my feature is also present in my samples. So this is what I came up with. Yeah, thank you so much.
I think that was the most important part of our debate today.
Yeah.
Me myself learned so much from it. These computational insights are fascinating. Let us now explore the chemical discovery revealed in your study. Your detection of flavonoids, phenolic, lignin, and terpenoids suggests complex ecological and botanical origin from a chemotaxonomic perspective. What do these metabolites reveal about plant source and environmental interaction?
Thank you so much, Heba, for that question. One thing I really had to conclude about was that most of these metabolites are linked to where these bees pick the resins from. So I can just project my next slide, which shows a picture of the different plant species. So like I said previously, like during my sample collection, and one of my field assistants here can testify, he was also very keen and interested in yeah, Jobline. He's also online here watching in his video there. So we did a lot of stuff, and we could record. So I went ahead because I also had that kind of I have a lot of experience in ethnobotanical survey research, ethnomedicine. So I was also interested in seeing how these resins link together to the chemistry and also later on, of course, the activity. So I started in our discussion. I realized that there were a key number of species which were like mentioned in most locations. And these were the Asteroshi, the Rubiaceae, Phoebiaceae, Cupraceae, Fabaceae, and Acadeaceae, and Malaceraceae. So this is for eucalyptus. So eucalyptus, I could say some of the proposed, not confirmed, but proposed. So more studies can go and do that, document or confirm using DNA, barcoding. But at least this is some of the list of some of the plants I at least assume or believe could be contributing to the chemistry or could be linked, and many more others which we may not be knowing, at least which maybe were not mentioned by these beekeepers. But for example, eucalyptus, this is a principal one, has been reported everywhere, and also coffee species, bees visit these flowers. Then a Euphorbia tirucari, you can see here, this is a Euphorbia tirucari. You can see a bee picks some maybe pollen or maybe picks some nectar from there, and also you see when you look at the Euphorbia tirucari plant, when you cut it, it normally oozes out sap, white sap. And there was a video I saw, and bees were picking sap from that plant. And this plant was mainly located in some districts, for example, Bushenyi, Nakasongola, and also some places in Masindi. So another one was the Mangifera indica, Albizia coriaria, this Malukia citrinus, which was used to be called citrinus, this bottle brush. Then also species in the pine family. Those ones used really to provide a lot of resins. And indeed it is true, when you read in literature, you find that most of the compounds, for example, the diterpenoids, are related to the resins which have been detected in these species. So I went ahead to compare and see, for example, whether these in literature, of course, whether some of these species have these components like isolated out of them. And indeed, you could relate and find, yes, a certain maybe class of diterpenoid X has been isolated from that resin. So that kind of connection was really important. So in most of the papers, I had to connect the two and link and create a link for the future for those who really want to confirm this through DNA barcoding or any other studies. Yeah, thank you so much.
Chemical diversity often reflects biological and environmental influence. Let's now examine your statistical interpretation. Which multivariate statistical tools were applied, and did PCA relieve a distinct clustering pattern among samples?
Okay, thank you so much, Heba. First of all, there are quite many types of, there are many softwares you can utilize to do multivariate statistics. In this case, for me to come up with that kind of, remember in my mind, my goal is to see whether geography contributes, So in this case, the chemometrics part was really important to come up with this. I just wanted to see the kind of loadings, the kind of separation among these samples and also in some districts. So as you can see here, I use the software called Metabolomics, which is a free software and it's online. You can always access it. Yeah. So, but this software uses, of course, in this case, I use the areas, peak areas. So now I got the peak areas from my putatively confirmed compounds, cross-referenced from MZ-mine with GNPS and SIRIUS. That should be very important. Not everything was which was matched, I mean, putatively identified was included here. I only used what was cross-referenced with the feature list from MZMine. So, of course, within this software, which is the Metabolomics, you do a lot of performances. There are a lot of processes you do, the statistical processes like data normalization, data scaling, for you to really have a good representative of your raw data. So, and also there are also different techniques within this metabolism or within chemometrics, such as PLSPA, which is kind of supervised. So I didn't use PCA because it's non-supervised. So I used PLSPA, which is supervised, which of course gives better results. And then I also use the orthogonal PLSDA, which helps you to go further basing on what you got from the PLSDA. So if there was some kind of like overlap in your PLSDA, you can also always do orthogonal, which involves like pairwise matching. So you do pairwise comparison of, for example, districts from Kotido and maybe Mbarara samples. So you see if there is a kind of difference between them. Then also I had to do heat map clustering, hierarchical clustering, and this was really important to come up with the aspect of fingerprints, like chemical markers, to see, okay, in district X, which profiles are present there, which profiles are more abundant there by looking, of course, at the key, and you look at the different abundances. Then I also looked at the biased sparse spatial correlations, which is like a network which helps you in creating biological, like it mimics a biological relationship amongst your metabolites. Most of these metabolites are related, so it gives you like a clue on the probable biosynthetic pathways which could be present between these compounds. So this is what I perform. So here you can see there are two plots. The first one is the one for compounds which were annotated by GNPS. Then B is the one which was annotated by SIRIUS. So you can see, I will just mention the key points. You could see these are kind of separated. This one's separated, this is also separated, but you find that there is somewhere these are surely creating like a cluster together, meaning that there is a lot of shared chemical constituents within these samples here. So this means that it's kind of different. And indeed, if you see, this is the same district and this is also the same district. So it means that there was a kind of variation among these districts. So there's also this, which was also kind of different. But if you look at inside here, the intra-group difference is not very much. You find that within the biological samples, for example, in the district, most of them, they are not very far from each other. So you can see the same here applies also here, but now there's a lot of a conglomerate formed here, which indicates similarity, in chemical analytes being detected. So indeed, it showed clustering patterns among the samples. Thank you so much.
In your opinion, Mr. Ivan, is the observed chemical variation primarily driven by botanical origin, environmental stress, or adaptive bee behavior?
Sorry?
The question again. In your
Okay.
In your opinion, is the observed chemical variation primarily driven by botanical origin or by environmental stress or just an adaptive bee behavior?
Okay. One, I think it is actually both. It could be bee behavior and also botanical, and also the origin. But of course, like I said, different species thrive in different agroecological regions. So it could be both. So for my case, I will keep saying this. I was looking at location. So I was not looking at the B pattern. So I have to be clear with this. So, but of course, as you look at your data, your data starts to answer some other questions which come up. Like it started answering questions related to whether botany or botanical species contribute to chemistry. So I tackled the bits part of it, but my main was surely geographical location. Thank you so much.
So understanding chemistry naturally leads us to a biological implication. So our next question: what motivated you to explore antibacterial activity computationally, and how were the biological targets selected?
Okay, thank you so much, Eva. Of course, after screening, after of course doing all the screening, and so I had to sit down. First of all, I don't like repeating what has been done. That's something I don't like. Like doing something which is already there. We already know it has biological activity, so I don't like always repeating it again. You know. So in our studies, okay, I think. Oh, I think I was supposed to do something related to this. This was the next question, I think. Yeah. 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 Sorry. So our chemical variation, you can see. Yeah. Yeah, I think this will be answered, and then the next slide will also answer that. Yeah.
No problem at
So
all.
I can start with the chemical variation. Yes. So this is a heat map. You can see this heat map. I tried to make sure that I only chose 45 best metabolites. So within metaboanalysis, you can choose, and it's recommended that you don't do a lot of them. Like you can choose the target. But for my case, I had to choose 45. You know, so some go up to 30, some go up to 20, some go up to 100. So for me, I had to say 45, top 45. So this was something I got. So I had to cluster this. So you can see these are districts. You see, this is Mbarara, this is Rwampara, this is Bushenyi. So these districts, this and this, most of them they are like close to each other and in the western region of the country. That's Uganda. So you can see the distribution here was mainly highlighted to be terpenoid rich. So you can see that geography, the chemical variation is also, if you go back from the other slide, if you get back the other slide, you can also tell that the chemistry depends also on the botany, where I said most of the botanical species in these districts were like contributed to many terpenoids. So you can see now there was a district here which is Adjumani, which was rich in flavonoids. So there was also another district here, which is, for example, these were three: Adjumani, Kibuku, Lida, and Masindi. These ones were very rich in flavonoids also. So then there are some, of course, simple small compounds which are also specific to some districts, meaning that that could be due to specific botanical contribution which is present in that given area and which may not be present in another area. So this was for GNPS. So if you go to the SIRIUS generated putatives, so you can tell here that you can see Bushenyi, Mbarara, Rwampara had a lot of phenolic compounds and also lignans. For example, hydrocinamic acids, which are actually detected here. So there was also steel rich. So for the steel rich, you can see it was mainly present in Cotido, this place here. So not present in this, not present like this is like in relative abundance. So it's not quantitative, like it's relative abundance. So you can see the more the red, the more the abundance. You can see as it goes to negative, it means the abundance is not very much in that given location. So you can see still in Nakasongola leader, this now Sirius, you can see it has a lot of flavonoids. So if you look at most of these, they're actually similar. So you'll find that in these districts, they are like shared. Some have shared botanical origin, some have like unique botanical origin. So for the environmental stress, this of course depends on climate and what kind of factors are going on. For example, you may find there is a lot of agriculture going on there, industrialization going on. So those are all, to me, I think those are all gaps you can explore. For example, the chemistry of propolis in maybe an industrialized area, propolis, then this the adaptive behavior, that can also be another type factor to look at independently. But in this case, mine contributed mainly to location, but to some extent the botany. Then if you go deeper, why did we choose antibacterial? So after our analysis, I did a literature search actually. So I did a detailed literature search like for a week on each metabolite to confirm whether there is, a given activity or reported antimicrobial activity of this compound which has been annotated. So I came up with a list of 28. Yeah. So about 28 of them had detailed, and some of them were scanty, like they're only reported, like assumed. Maybe it could be due to this, it could be due to this in the literature. But most of these were like performed on, like the on individual isolated compounds. So I had to exclude this because it was not. I really wanted to work with new annotations to see if maybe they also have potential antimicrobial, targets. So you can see also in this annotation, there's the who are lucky. Like rutin was also detected in both GNPS and SIRIUS. Luteolin, which is also a common flavone, detected in both tricetin, purulin, and many others. So now, how did we choose? So I had this out of my data. I had to go back to meta-analyze and excluded all these. After now doing my literature review, I had to exclude all this from my metabolites. Went to meta-analyze, performed everything related to it, such as normalization, scaling, etc. So I had now to choose. How did I select? So first, these are two heat maps. One for SIRIUS, one for GNPS, and one for SIRIUS. So I had to look at, is this compound present in both annotations? Yes, if it is present, I would choose it. Number two, is this metabolite distributed? Is the abundance present at least in 3 locations? Yes, I would choose that. Then another criteria was, is this metabolite kind of unique and strange, like a strange diterpene? There's something you look at and it's kind of strange, not reported anywhere, and you in proposal and you want to see whether it has something. So that was also a criteria, but the list. But the first two were like my main criteria. So that's how I had to select my metabolites for my next study. Thank you so much.
Okay, our next question: among the detected metabolites, which structure or physiochemical features contributed most significantly to strong docking interaction?
Okay, thank you so much. I just picked a little here. In case you want to get more of the details, you could go deeper and download the paper and read the supplementaries. So one is we picked, after doing that, we picked some of the compounds, around 7. I'm happy to have also collaborated with a team of colleagues who are also present on this call from Uganda, and we performed this, of course, on selected the proteins. So how did we select the proteins? So These proteins were also selected based on the resistance pattern of pathogens in the Uganda, by the way. So I had to go back to literature and check which, microorganisms or pathogens are causing, the threat in AMR. So I had to choose. So then I went to my protein data bank, PDB, and of course, even during in literature, you read what you see what people have been using for docking, and some of these really proved to be like the candidates I could go for. Like Staphylococcus aureus, Bacillus subtilis, Streptococcus mutans, which mainly causes these dental caries. That was also one of the aspects because I was also dating back how propolis is being used. It's used for toothache issues, so that was one thing, you know. Then Klebsiella pneumoniae, this is also dated back. Normally, Klebsiella is involved with people who have upper respiratory tract infection. So I was trying to look at how this can be solved, but looking at what is causing what in Uganda. So this is how I selected all these organisms. So I did this. We did this with colleagues, and so this is a table which shows the binding energies. So you could see we also used some of the antibiotics, standard antibiotics as positive controls. So these are binding energies. So these are our targets and binding energies. So you can see our binding energies were kind of some of the binding energies, like for example, renotrine, cositron was kind of even better than the binding energies for the ciprofloxacin, for example, here in 3-AIC, which was Streptococcus mutans. So most of these compounds, which contributed to kind of better binding energies, as you can see from these 3D and 2D structures, were flavonoid related, those which were in the flavonoid scaffold type. So, and you could see this was supported mainly by the interactions between the amino acid residues, creation of salt bridges, a lot of hydrophobic pocket compatibility, then also the pi bonds, which could strengthen this kind of docking and hence increase the binding energy. So I could say at least the flavonoid type really gave out. Then there are also some this the tiglian terpenoid, which was kind of heavy and its binding energy was kind of not good. And we try to read and check that most of the time, if a molecule has a lot of hydrogen bonds and also heavy, like the molecular weight is really too much, it affects also the binding pattern, of these molecules, of these ligands with the proteins. Yeah. So this is what we did basically. Thank you so much.
Okay, Mr. Ivan, detecting the activity is crucial, but safety and pharmacokinetics are equally important. So, what insight did the ADMET prediction provide regarding pharmacokinetics, safety, and drug likeness of the identified metabolites?
Okay, thank you so much, Guts. So I just got screenshots of course, these are CSV files which are kind of big. You can't just put the whole of it here. I just took the screenshot of the most important. My colleagues and I, we did some of this ADMET. It is important. After docking, yes, you get putative, something which is promising. But again, in drug discovery, you need to look at whether what you're trying to come up with will it be really be like will it be undergo through all the approaches, like the safety approaches? Will it be absorbed, distributed, metabolized, and also excreted within the body? So there are in silico tools which you can do. So there's this ADMET predictions, which we also tried out, and some of these parameters, such as absorption, were performed. So you can see we performed some of this. you can see here on the excretion, most of them show the clearance. You can see the time here, the half time, for example, for ligand 4, which is quercitron, was 2 minutes. So this means the drug will not be like stay longer in the body. Like this compound, if it would be absorbed, it would not really stay longer in the body. But if you look at, for example, ligand number 9, which is a eudesimine, it took a lot of time here. They have time, 8 minutes. So to me, this would not really make it possible. It's like to me, it would not be nice to include such a thing into drug, design. Then also, I mean sorry, the half-lives here, actually here. Then you could also see some of the medicinal chemistry parameters such as these rules. Some of the compounds did not pass. For example, the Pfizer rule, Pfizer rule was passed for all apart from ligand number 6, which is sandalcopimaric acid, which is one of the terpenes. So to me, this would not also go on. But all in all, if you go to the safety patterns, the docking, the parameters indicated that, for example, renotrine, which had an lethal dose of 50, at least was in the range, in the toxicity class range. Then others surely did not really perform very well, and there as a drug discovery scientist who is using computational, which computational chemistry would actually now decide and say, okay, I will not include this into my drug discovery process. So if you look at the cytotoxicity, the toxicity part, you can see I picked a few here, like most of them were really, like for example, this ligand here, there's one which was inactive, meaning the immunotoxicity part would really not be dependable. Then the cytotoxicity, most of them were inactive, and so this raises issues. So yes, it may prove to be good in binding, and also, but the toxicity part is also important. So here you also have to decide as a scientist on what to take and what to exclude. So details of this can be found also in the supplementary files if you wish to really get into deeper ADMET predictions we did. Yeah, thank you so much.
Okay, Mr. Ivan, next question. Did any compounds demonstrate an optimal balance between bioactivity, pharmacokinetics, and low toxicity, positioning them as promising drug leads?
Yes, they are. Because if you look at the binding energy, I'll just take you back here. So from here, you could tell at least they are promising leads. Like I said, especially the flavonoids. The flavonoids scaffolds actually are promising. And surprisingly, I have done already some of the preliminary in vitro studies on some of the extracts. And I tried to connect my data with my chemistry with the in vitro currently, and I realized that some samples which had from my heat map, which had a lot of flavonoids and phenolic acids, like the abundances, are actually performing better. If you look at the zones of inhibitions, like they are performing better. So to me, I think the flavonoid and phenolics could be really contributing, but we I'm yet to discover more on multi-drug resistance, and also I really want to go deep and do the quantification. I see which sample has what. There's that quantification part where you need to look at the total flavonoids, total phenolics, total terpenoids, in these samples. Yeah.
So let's talk about the scientific and pharmaceutical impact. What is the broader biomedical significance of your findings, particularly in antimicrobial discovery that you mentioned here in your study?
Okay, thank you so much, Heba. Yes, once again, we had at least discovered multiple scaffolds, which of course could be lead targets for our next studies. And also there was a lot of structure novelty. If you check surely in literature, there are some compounds which were annotated in our samples, which are not actually in other propolis types. If you look out, you'll find that mostly they say European propolis contains mainly flavonoids, phenolics. But now, if you look at our profiles, it also has the terpenoids there. So if you look at Brazilian propolis, you find they have flavonoids, mainly prenulated flavones, and other types. But in our case, in the Ugandan propolis, we have really a lot which we discovered. So these findings surely, at least they show some structure novelty, compound novelty, and also the other part is, the part of the in silico gives us an opportunity to accelerate screening. So now at least we can go ahead and basing on what we have, we can look at samples to depend on. I'll give you another instance here. Like there is a sample in one of the districts which did not show any zones of clearance. Like there was nothing, there was no inhibition at all. So when I dated back and checked in my data, and I realized that um, this sample actually had abundance it was abundant in mainly steel beans and only terpenoids. So no flavonoids, no phenolic acids. So here now I can choose on what to go with. If my target is really to come up with antimicrobial drug leads. Well, it depends. If, for example, someone needs to do anti-inflammatory studies, terpenoids have really shown a lot of potential in anti-inflammatory activity. So you could now choose and say, okay, I'll go with samples from Bushenyi, Mbarara, Rwampara, or from the western side, which were kind of which had a lot of terpenoids. So then that leads to also the priority. So you have to choose. So here now I'm choosing. So I can choose, for example, samples which had this and this to go for my to qualify as my lead. So this is a picture here which is actually illustrating what I'm trying to explain. So from here you can choose and go to your antimicrobial leads. Thank you so much.
So your work also represent an important methodological advancement. What were the main limitations of your study?
Thank you, Heba. First, this was in silico. So especially for antibacterial, it was not in vitro. So that is a weakness or limitation. So there's need to confirm. More studies need to be carried out. So I'm now confirming this in my in vitro studies, and later on also discover some parts on antibacterial mechanism of action. Is it through formation of biofilms, destruction of membranes, cell membranes? So all this is going to be discovered later on. So the limitation was like this for the in silico. This was mainly in silico, and it did not deal with any experimental validation. So hence need for in vitro screening, which now we are doing. So the other part was these were annotations. So there are studies which can be done, to do NMR, like for example, nuclear magnetic resonance studies for structural elucidation. So you can confirm most of these structures. So for example, I plan, for example, if, for example, I'm interested in the anti-inflammatory, I can go and choose extracts for certain districts which showed abundance in terpenoids. Then I choose that and I confirm. I go maybe through isolation purposes, do a lot of fractionation, and then I confirm whether these flavonoids terpenoids are surely present. So then the in silico predictions, of course, require biological confirmation. That is something we're also doing. So the other part could be even the ADMET would need to do cytotoxicity studies in vitro. I love in vitro so much because I have I respect animals so much. So, but of course, later on, bigger studies can go further to confirm this in different biological systems. So this picture shows also what I've been talking about. So these models, the machine learning models, can give you a lot of leads, but later on, you need to choose. You know, some do not qualify, some qualify, and you need to choose what to go with for your studies. Thank you so much, Eva.
So our last two questions was very interesting, by the way, Mr. Iman. Looking forward, your work opens exciting future direction. What are the next step in your research following this study?
Thank you so much, Eba. Firstly, there is this heat map which has a review on the I think composition of propolis. So when I checked this, I didn't see Uganda there. So I would be happy to do a review, a review and update, update Ugandan chemical composition in this. So this review has a lot, Ethiopia, New Zealand, Cameroon, Argentina, Thailand, Europe, but Uganda is not there. Okay. So I would also need now to do quantification of chemical markers, marker groups, like I said before, then validation of antibacterial assays, then expanding the library. So if you could pull out, because I'm interested in Africa here, Algeria is doing well. The database, then their libraries are good. They have already flavonoids, aromatic acids. This is pulled out of this. Cameroon has reported a lot of triterpenes. Libya has lignans, terpenes. Egypt. So this is my host, my host people today. So you can see, you have a lot. You've done a lot on propolis. There is a lot on propolis. Ethiopia has also a lot. Kenya has also reported a lot. But Uganda, we didn't have anything. So now the yellow highlights is something I picked from our findings. So from our work, both the GCMS, headspace, GCMS, and volatiles, then LCMS for the non-polar and polar, at least we can be able to confirm that there are some of these classes which we could include in the as chemical components present in Ugandan propolis. So this is something I would really really be happy to do next. Thank you.
All the best for you, Mr. Ivan. Our last question. How do you envision AI, the computational metabolomics and molecular networking, shaping the next generation of natural product drug discovery?
Okay, thank you so much. Um, Now I just want to. I think I should hold on a bit. Yeah. So now AI. This is not on the slides. I will just say it. So one thing is we need to, as scientists, we need to embrace is the technology, and the things are changing. If we are to surely proceed with research, we need to learn different techniques. For example, those days, one of my supervisors used like to confirm. You confirm metabolite by metabolite. You look at the stereochemistry. You look at the bonding pattern. By hand. Now AI has come up with a lot of techniques. Now it is being incorporated in even instruments. Like if you check the new upcoming instruments, they're at least incorporating some possibility of having some metabolites which have been detected through machine learning. Here, if I say AI, most people think it's Chat GPT. It's beyond Chat GPT. It's it's also machine learning as well included. So people are now using machine learning to incorporate fingerprints which are online in published data to come up with databases. All these databases. So we are utilizing this as a matter of using AI or machine learning. So we need to embrace that. Yeah. Thank you so much.
Well, the thanking is to you, Mr. Ivan. Looking forward. Uh, Before we conclude, I would like to express my sincere gratitude to our distinguished speaker for this enlightening, insightful, and inspiring discussion. Your valuable contribution and scientific vision truly enrich this session and deepen our understanding of modern metabolomics and natural product discovery. I would also like to warmly thank all attendants, colleagues, researchers, and students who joined us today. Your presence, engagement, and interest are what make scientific dialogue meaningful and impactful.